Hey there, and welcome to this explainer. Today, we're diving right into the deep end of data. We're going to set the stage for a really fun, structured look at the two absolute superheroes of statistics for ungrouped data, the mean and the median. Honestly, whether you're staring down a giant spreadsheet or just trying to figure out your average test score for the semester, you absolutely need these two tools to make sense of the numbers around us. So, let's get into it.
Okay, let's dive into this. Have you ever wondered how you summarize an entire crowd with just one number? Imagine looking at a room full of people, completely different heights, ages, backgrounds, the whole shebang. How do you boil that wildly diverse group down to just a single representative value? Well, that's the real-world challenge of central tendency. It's the ultimate quest to find one clean, simple number that speaks for a whole messy pile of information.
To get us there, we've got a pretty straightforward roadmap today. First up, making sense of the mean. Second, we'll look at the mean's hidden math hacks. Third, fixing a broken mean. Then, mastering the median. And finally, we'll wrap up with the odd and even rules. Don't worry, we're going to break all of this down logically, step by step.
All right, starting off with Section 1, Making Sense of Mean.
You can think of the arithmetic mean as the great equalizer of data. It is all about achieving perfect mathematical balance. And the formula? It's super simple. The mean, which you'll often see written as an X with a little bar over it, is just the sum of all your observations divided by the total number of observations. Oh, and just a quick heads up, mean, arithmetic mean, and average literally mean the exact same thing here. Totally interchangeable.
Let's actually anchor this formula in a real-world example so it makes sense. Say we're looking at the heights of 6 boys measured in centimeters. We've got 146, 154, 153, 160, 157, and 160. To find that single magic number that represents the whole group, we just apply our rule.
We add up all those individual heights, which gives us a total sum of 930 centimeters. Then, since there are 6 boys, we just divide that 930 by 6, and boom, that leaves us with a single, summarizing mean height of 155 centimeters. It's neat, it's precise, and it takes every single boy's height into account to find that exact balancing point.
Moving right along to Section 2, Means Hidden Math Hacks.
And what's really interesting here is that these properties aren't just boring rules to memorize. They're actually brilliant shortcuts. Take property 1, for instance. It reveals this foundational secret of statistics. The sum of the deviations of all observations from their mean is always exactly 0. Seriously, if you measure how far every single data point is from the mean and add all those distances together, you will hit absolute 0 every single time.
Let me show you this magical zero-sum balance in action. Let's say our numbers are 4, 5, 7, 9, and 15. The mean of those is 8. Now, if we calculate the deviation, meaning we subtract that mean of 8 from each number, we get -4, -3, -1, +1, and +7. If you add up all those negatives, you get -8. Add up the positives, +8. Put them together, and 0. The numbers below the mean perfectly offset the numbers above it. It's just perfectly balanced.
And the math hacks don't stop there. Let's rapid fire through a few more of these. If you take a dataset and increase every single observation by a certain amount, let's call it A, the mean automatically increases by A. If you decrease every observation by A, the mean drops by A. Multiply every number by A, the mean gets multiplied by A. Divide every number by A, yep, you guessed it, the mean is divided by A. The huge takeaway here is that whatever uniform operation you apply to your data, the mean automatically follows suit. You don't ever need to go back and recalculate the whole entire set from scratch. It's a massive time saver.
Okay, on to Section 3, Fixing a Broken Mean.
So, we know the mean balances perfectly, right? But what happens when human error gets in the way? Let's say you have a massive data set. The mean of 40 observations is 160. But, you realize a typo snuck in. One value was wrongly copied down as 125 instead of 165. So how do we fix the mean efficiently without having to start over and re-add all 40 individual atoms? Because nobody wants to do that. Well, we just walk through a few very logical steps. First, we find the incorrect total sum by working backward. 40 observations times the incorrect mean of 160 gives us a total sum of 6,400. Second, we subtract that bad data point, so minus 125. Third, we add in the correct data point, plus 165. That gives us a brand new corrected total sum of 6,440. Finally, we just divide that new total by our 40 observations. The result?
a true corrected mean of 161. This proves you only need to adjust the overall sum, saving you immense time and effort.
That brings us to Section 4, Mastering the Median. Now, while the mean is obsessing over perfect arithmetic balance, our second statistical superhero has a totally different vibe. The median cares entirely about position and order. By definition, it's simply the value of the exact middle term in any given set of data. If you line everybody up in a row, the median is just the person standing dead center. Half the values are above them, and half the values are below.
But to find that center, there's one absolute non-negotiable rule you've got to follow first. Step 1, you must arrange your data in ascending or descending order. If your data isn't sorted, your median is going to be completely wrong. No way around it. Once it's sorted, step 2 is to count the total number of observations, which we call n, and step 3 is just applying the right formula based on whether n is odd or even. Honestly, just treat this as a simple procedural checklist.
And finally, Section 5, the odd and even rules. And this brilliantly illustrates how finding the middle splits depending on how many data points you actually have. When you have an odd number of items, say 5 items, an exact middle exists. It's the third item. The formula is simply the value of the n plus 1 divided by 2 term. But when n is even, like 4 items, there's no single middle. 2 numbers actually share the middle. So you have to find those 2 middlemost numbers, add them up, and multiply by a half. Basically, you're just finding the mean of those 2 middle terms.
Let's look at a quick side-by-side comparison to see these formulas in action. For the odd example, say we have 11 items. 11 is an odd number, right? Following the formula, 11 plus 1 is 12, divided by 2 is 6. So our median is the exact value of the 6th term, which happens to be 31. Now for the even example, say we have 10 items. The middle is actually shared by the 5th and 6th terms, which are 47 and 49 here. The average of those two gives us our median, which is 48. Pretty straightforward.
So what does this all mean? Why does this actually matter? Well, think about looking at a bar graph of real-world data, like population sizes, across different municipalities. You might see some soaring way up to 1,800, while others dip down to just 400. Mastering the precise differences between the mean and the median gives you the analytical power to look at a wildly uneven distribution like that and know exactly which mathematical tool to reach for to make sense of it.
Which leaves us with a final, provocative question for you to ponder on your own data literacy journey. In a messy, real-life data set filled with extreme highs and extreme lows, which measure do you think is more trustworthy? Is it the meticulously balanced mean or the positionally secure median? Keep that in the back of your mind the next time you're looking at the numbers. Thanks so much for joining me on this explainer, and hey, keep questioning the data.